So, all right, so homework one. So the first type of question on here, in general, is what's called area between curves. So depending on who teaches you Calculus 1 and depending on how far you get, you either did or didn't cover this in detail. So when we taught it last semester, we got through it, but it doesn't hurt to just sketch the idea again. So look, the most general problem of all time is if I have a curved region, how do I assign size to it? Now, that's actually a very difficult thing to do. Assigning size to regions in the plane is not easy. In fact, there's a whole branch of math dedicated to that called measure theory, which is really about assigning size to objects. Now, you might say, well, what do you mean? This is easy. We talk about area when we're kids in school. Yeah, you did, but you talked about area of rectangles. You talked about the area of a triangle, some polygons. But what you didn't really do is, because it's really difficult, is you didn't, if I said to you, what is the area of the region enclosed here? How would you begin to A, define what that means, and B, if you have an effective definition, how would you compute its value? So let's label this picture. Let's label this quote unquote hard problem. But if we phrase it a slightly different way, if I phrase it by doing this, by introducing, if I look at more specific cases, for example, if I say, okay, let's, instead of just some arbitrary shape, let's say I have a coordinate system. And instead of some region like that, let's suppose I have some curve that has some algebraic equation, y equals f of x. Now, that's another way of saying that we have some function and we're going to consider its graph. Excuse me. Now, what we learn in Calculus 1 is that if I restrict a certain region in the plane, and let's say I look at the lines A and B, and then I say, okay, this shaded region, this problem is not as hard, so let's label this easier problem. I'm not going to call it easy, but I'll call it easier. Problem. So what is the area here? Well, the area we learned from Calculus 1 is defined to be this integral. So let's take a moment to think about this. In the hard problem, I just have some region that has a curved boundary. I know nothing about it. Whereas in the easier problem, I have a very specific type of region. 3 of its sides are straight lines, and 1 of its sides is the is the curve of a continuous function. So the harder problem we can't do yet, but we can do a simpler and easier problem. And then these ideas from the easier problem can be generalized a little further. So now let me draw another picture, and let me sort of get you to imagine it this way. Now imagine instead of having one curve, suppose now I have a curve. We'll call this guy y equals f of x. But suppose I have some other curve too. And let's call this guy, for a lack of a more creative name, we'll call him g of x. And then let's assume we have two curves, one where the one curve is always above the other. And then we just pick our, say we have 2 points. Let's say this is A, and let's say this is B. Then what we can do is we can look at this region as well. I'll call it green. So if I shade the region between the curves, a la area between the curves, so it turns out that the green region has area. You take the top of the boundary, which is f of x, and then you subtract the bottom boundary, and you just integrate what remains. It turns out that if we did some Riemann sums and we chop this, region up into rectangles, that's what we get. So the way you could think about this is we are defining, really what we're doing is we're defining the area of that green region as this integral. So then if you're a skeptic, you can say, well, why would we define it to be some complicated thing? Well, don't forget, if you put your time machine on in your brain and go back to Calc 1, don't forget that when we set out to define a notion of size, our integral was motivated by using intuitive size. And what do I mean by intuitive size? Well, the area of a rectangle, its length times its width, is very intuitive. And so if we're going to generalize the notion of size to curved regions, then it better still be that our new definition of area, which is this rectangle, this integral, it better agree with our old notions of area for rectangles and triangles. And I know, at least in my courses, we spend a lot of time in Calculus 1 trying to convince you of that. So if I go back to the previous slide, this problem here, the hard problem, we are still unable to solve this in Calculus 1 or 2. It requires a little more ingenuity. However, we are able to easily now solve a region that has one curved boundary, or two curved boundaries. Now, Paul, what happens is, in the example that you are sort of alluding to in problem 7, is that sometimes the region we're studying is even more complex, and we have to deduce a way to reduce our very complex region into one of these simpler regions. Does that make sense?
Yep, so far so good.
Yeah, okay, so for certain regions, we have this, it's rather straightforward, provided you know how to integrate.
Yep.
However, we get to a point where if the region is more complex, then things are, how do we say, more complicated. So what I'd like to do on this right-hand side is just get you some hints for the first couple problems. And if you need help, more help with them, let me know. But what I'd like to do is I'd like to, work out some of the more complex ones, just so we're all on the same page. So if what you could do is you can, if you look at your homework, let's look at number 5, for example. Let's go real briefly. If I draw a coordinate system, and what I'm going to do is I'm going to draw two curves. I'm going to draw, the first curve I'm asked to draw is x squared, and I'm also asked to draw the curve square root of x. And so look, these are very elementary functions. If you're in Calculus 2, you should not need a calculator to graph 5 or 6, or frankly 7 or 8 for that matter. Now, it's not wrong for you to use a calculator to convince yourself that what you did is correct or to verify, but you shouldn't need a calculator to graph x squared. If you're in Calculus 2, you should have had enough experience to know what these basic graphs are. And so what does the square root function look like? The square root function's graph looks like this. So this is y equals the square root of x. And if I'm going to be very careful with this, let me switch colors and let's try to draw this as nice as we can. This is 1 and this is 1 on the y-axis. Then what does the graph of x squared look like? Well, I'm not interested in what's happening when x is negative because it's immaterial. The only region that makes sense to my problem here, and it might take some time for you to think about this, the only region that makes sense is this green region I'm shading. It is the only place in the plane that you can say is bounded by these two curves. If I look up here where my pen's floating around, there's no bound here. This is a region that goes on forever. This goes on forever. Up here goes on. This is the only thing that's bounded between two curves. And so let me be very clear that this intersection, I might not have drawn it as good as it should be. This point where they intersect is the point 1, 1. And so here, if I want to compute the area of this region, the area is the integral from 0 to 1 of the top, which is the square root of x, minus the bottom, which is x squared dx. And this is a very straightforward integral. We did some examples like this last class. So you can finish it, or at least try. And if you need help later, I'll help you. Does this make sense?
Yep. Yeah, I got an answer for that one.
Yeah, so this is a very simple example, but when I use the word simple, I don't mean that humans get this right away. I mean that it's simple in context. If we're going to talk about problems where you compute area, this is about as simple as it gets. Some of the other ones, if you've tried them, you'll see they get much more complex. Let's do the next one, because this is also one that you could use some sort of help sketching these things. So the next one, if I draw my plane again. So I need to graph x cubed, and x squared. Now, what makes this difficult is oftentimes as amateurs, we often forget how these graphs behave between, say, 0 and 1. So here's a good thing to mentally do. Take a number between 0 and 1, say a half. When you square it, you get a fourth. But when you cube it, you get an eighth. So when you're drawing these guys, the square function, which is going to look like this. That's bad. That looks like a line. This is our y equals x squared. And the cube function, believe it or not, what was I using? Purple? I'm trying to be consistent. Or pink. I was using pink. The cube function actually comes up like this. and then it's underneath it until it beats it out at 1, 1. So this is usually something that when we're first learning these things, we get a little confused about. So the only area that we're interested in is this tiny little sliver that I'm going to shade green. So the area here is the integral from 0 to 1 of the top guy, which is x squared, minus the bottom guy, which is x cubed, dx. And again, that is a straightforward integral that you should know how to do without help, so I'll let you do it. Does anybody have a question about this? By the way, let me label this x cubed here so we're all on the same page. So my advice is for you to study these elementary examples right here, because it's really difficult to do the ones down the page when the algebra gets more complicated and the geometry gets more complicated. So think about if you have a question, and please ask if you do about these problems. And then I want to show you something before we do the other ones. We're building up to 7, if you will.
Sounds good. I'm good with these ones so far.
So if I can do a sort of a quick little very off, I don't know if that makes any sense, but show you something. So one thing, most of you have seen this before, but maybe Paul, I don't know if you have or haven't, I forget now. What I'm going to do is I'm going to share one of the best web pages there is that's free, and it's called Desmos. So if you just Google Desmos, I put this on the syllabus. You can download it on your phone, your iPad, your Samsung. It's free. Here, it gives you a good way of making sure and verifying. Here's your x cubed. So I can graph that. I can graph my x squared. And you'll see the picture that I got is that I sketched by hand is same thing that we have here. So the region that we were interested in was this little region in here. Now, why do I point this out now? Well, I'm pointing out Desmos now, Paul, because if you look at problem 7, sketching this region is a little more tricky if you don't have great ideas of the exponential function and how it grows. Whereas if we go to Desmos and we graph those functions, so what's the first one? It's e to the x. And then the other guy we were dealing with was 2x plus 1. And what you'll notice is the region, as you alluded to, is a little more complex. So if I change my bounds to change my window a little bit, what I find is this. So the other line we had was x equals 2, I believe, right? Is that what I said? So I'm gonna zoom out a little more. Can I annotate this? I think I can. So the region that we're interested in is actually this region right here, this sort of curved sided triangle, and then this little flower petal. And so what makes this problem tricky is that in order to do it, we have to realize that we need 2 separate integrals, one for the first region and one for the second region. Now, why am I saying 2 regions? Well, notice, look at the curves. On the first region, the top is the blue line, and then it's the red curve. And the second part, it's the red curve is above the blue line. So, Paul, I think you alluded to this. The key thing in this problem is to figure out where do they intersect if you want to solve this problem correctly.
Yep. I was using the Desmos, and you can see where they intersect. My question
How do you
was
do
just
it precisely? That's what makes this problem challenging. So let's look at that. So let's go back to our whiteboard. So here's what we have. Let's draw a picture, and we don't even need to use Desmos. We can use some deductive reasoning. So let me, I'm not, and again, no one's expecting you to, no one's expecting you guys to reason it as quickly as maybe I will. And that's okay, no one's expecting you to. So here's what I want you to think about though. I want you to use basic ideas of this thing. So I'm gonna draw my XY axis. Now, I'm not going to draw it to scale like I did the other ones just because, well, straighten out line. Just because it's a little more difficult to do that. So before I draw my exponential function, what I want to do is I want to draw my line. So actually what I'm going to do, this is actually a better idea. I'm going to draw everything in black at first. So here's my exponential function. What do we know about the function e to the x? Well, we know that it intersects at 0. We know at the point 0, 1. Well, that's ugly. Oh my God, my kids are fighting up there. You guys hear this? Kids are acting like animals up there. So we know that the exponential curve does this. I'm going to sketch a dotted line at first. Comes up like that. Now, we also know that our line is y equals 2x plus 1. So that is a line of slope 2. So I'm going to use this blue here. That is a line of slope 2 that also goes through this point. So that line goes like this. So right now I'm doing some reasoning. Notice I'm doing dotted lines because I'm trying to figure out what's happening here. So the next thing I do is I say, okay, I think I have a good idea. And also you could have gotten this from Desmos. All right. So now I'm going to erase this. And I'm going to try to get a more accurate sketch of what's happening so that I can reason what's going on. So the next thing I'm going to do is I'm going to take this blue guy and I'm going to draw a line. Now, this is my line, y equals 2x plus 1. Now, I'm going to draw my exponential function. So I'll use a different color. Maybe I'll use yellow for that. My exponential function is going to come up like this. It's going to be lower than the blue line, and then at some point it's going to surpass it. So the region that we're interested in is this green region here, and then we're also interested in the green part comes over here a little bit. Now there's some important things I can label. So I know one place is here. I know another point of intersection is here. And then over here somewhere I know is 2, and I know that I'm going to stop at 2. So here's what I know. Just doing some deductive reasoning. I know that my area is, let's say, region 1 plus region 2. So I'll call this one 1, and I'll call this piece 2. And so region 1, what is the integral? Well, it's going to be the integral from 0 to something. What's the top? Well, the top would be 2x plus 1 minus the bottom, which is e to the x. And then the next piece is going to be the integral. I'm going to leave it blank for now. It's going to be e to the x minus 2x plus 1. So the missing piece is, what do I have here? because I know what the other bounds are. I was given them. Now, of course, if you go to Desmos, and I'll go there in a second to show you something. Before we do that, does anybody have a question about this so far? Anybody? Going once? So if I go back to Desmos for a second, I can estimate that by clicking on it. If I click on Desmos is pretty smart, it'll give me the decimal approximation of where they intersect. But that's not going to give you the exact answer. That would just give you a good approximation of the answer. So what we'd like you to do is be able to do it exactly. So in order to do that, what you have to do is figure out this point. What is this mystery point? Well, in some problems, it's easy. In this problem, it's not. I shouldn't say it's not, but you have to be a little creative. So what is question mark? Well, question mark is equal to the solution of e to the x equals 2x plus 1. Does anybody have a question about this? Now, the ultimate question is if you did this problem, then you're going to say, how do I solve this, right? All right, so let's think about this. Can we solve this? Exactly. That is, can I do some sort of symbolic manipulation that tells me exactly what x should be? Where are we at? Am I sharing the screen? Yeah. So, Paul, I knew this was a long way to get to your question, but I'm assuming this is where you were at when you originally asked the problem. Is that correct?
Yep, that's where I was at.
Yeah, right. And that's why this problem is assigned. Can we solve this? I mean, you might go to a computer and they'll solve it. You might know that there is an exact, I mean, look, clearly if I plug in, there is one solution that's easy to see. The first solution is if I plug in 0, we get a solution. So let's make note of that. Clearly, x equals 0 is a solution. Now, the graph tells us there's another one, but we don't know exactly what it is. And if you think about it a little more, you'll say, maybe I can't solve this by hand, because if you remember how you deal with log functions, the way exponentials is you have to invoke its inverse. You have to get rid of it by taking a log. And if you take the log of the left-hand side, it'll kill the e, but then it introduces just as something difficult on the right-hand side with a logarithm. Okay, so what do we do? So turns out the other solution is x approximately 1.25643. How do I know that? Well, I can use a computer to figure it out, or I can go to Desmos and estimate it. The problem is, in order to verify this, we need tools. And if I'm not saying you had to do this, but if you remember back in Calc 1, we did this thing called Newton's method. So what did I want? What was the purpose of this problem? So instead, we could use a calculator like Desmos to approximate. So if you wanted, just to sort of put a bow on this problem, the area we're after could be approximated very well if we just integrated from like 0 to 1.25. Whoops, that's sloppy. Of 2x plus 1 minus e to the x dx plus the integral from 1.25 to 2 of e to the x minus 2x plus 1 dx. So what I'm trying to tell you is in this particular problem, we cannot get an exact answer. We can only get an approximate answer, which is kind of like a pretty interesting fact. Now, we can become as approximate as we want just by getting, you might remember Newton's method can tell us we can get a better and better approximation of where they intersect. And if we use that better number, we'll get a better and better actual approximation of the area. So this is a very challenging problem, but it also reminds you of some delicacies that we don't always get exact answers. So hopefully you take this problem as a learning experience. Does that make sense?
Yep.
Now, in most of the other problems, I believe that's the only one where this is an issue.
Yeah,
so
that was the only one that I saw.
So you might say, Paul, well, why wouldn't you make that last since it's different? Well, we can't always get under the assumption that the first one's the easiest and the last one's the most difficult.
I just thought 7 was a special number.
Well, it is. It's a prime number. And there's 7 days in the week, too. Don't forget it. Does anybody have a question about this? Problem 7, at least. Yeah, so this brings up an important idea in advanced mathematics and science and engineering. This idea of approximation. Many things in the real world we cannot compute exactly, and we have to determine how to approximate it. And then we also have to determine how accurate is our approximation. That is an important theme. In fact, there's a whole branch of math that dedicates itself to that. It's called numerical analysis and scientific computing, where, solving very, very complicated things using computers or algorithms. And then once we solve them, we have to determine how accurate our approximations are. And we'll talk a lot more about that in this semester as well. So I'm kind of foreshadowing this approximation idea right now in the first homework. And you've seen it already. I mean, we started this with Calc 1. We approximated integrals with Riemann sums. If you remember, put your time machine on. All right, does anybody else have a question about 7 before we move on? All right, so then the next question you had was 10. So let's look at 10. So number 10 deals with what I mentioned on Tuesday, this idea of motion along a line. So what does that mean? Well, I'm telling you a ball is tossed straight up in the air. So if we just ignore things like wind and air resistance, we imagine that that ball goes straight up, gravity fights, and eventually gravity wins and the ball falls back down to us, right? So that ball moves up and down in a straight line. And so what's fascinating is that we can model this sort of ideas. We can use mathematics, we can use calculus to model and predict how this ball will travel. Now, when you were a student in high school algebra, one of the things you learned about when you were studying quadratic equations is they said, okay, we're going to do some applications, and this is one of the applications they would do. They would say, okay, here's a falling object. And you might have solved problems like if a quarter is dropped and it makes a sound in 3 seconds, how deep is the well? Or you might have solved problems like where a toy rocket goes up in the air. Here's the equation that tells you how high it is. Find out when it hits the ground. So we tell you in algebra that quadratic equations are the best equations for explaining things that go up and down, but they never tell you why. And the reason they can't tell you why is because it requires calculus. So you now know enough calculus that you can figure this out. So here's what we know. And you might also know this from physics, that if we have acceleration, again, I don't want to get too much physics into it, but you guys have heard of Newton's law, I'm almost certain. His second law, especially, that force is equal to mass times acceleration. And if I am throwing a ball in the air, there's no external forces other than gravity. Gravity is the only thing acting on this ball. It's trying to pull it down. And so what we have is we have acceleration due to gravity. And this is the only force on the ball. Okay? So what is gravity? Well, gravity is often, we can calculate it. So by basic physics, and again, you might just have to trust me if you've never had physics, our acceleration is equal to gravity. And in this particular case, it's either negative 9.8 meters per second squared, or what I usually round it to is negative 32 feet per second squared. So the key observation here is that it's constant. So we know this ball is accelerating, at least if we trust the theories of elementary physics. When you throw it from your hand, it decelerates until it's not moving at all, and then gravity starts taking over and pulls it back down to the ground. It has the same acceleration. It's constant. Okay, so here's what we know. Back in Calc 1, we studied that if we have something moving along a line, its displacement tells us where it's at. And then if we take that derivative, that by definition is velocity. So here's what we know. So from Calc 1 or physics, depending on when you want to think about it, here's what we know. We know that height this has velocity v of t, which is the derivative of h, and it has acceleration which is the derivative of velocity. So that's the properties in terms of derivatives. Now, if I have, there's like chaos going on. You guys hear this? People yelling. What's going on? My house is like a party zone. We can rephrase these now in terms of integrals. So let's think about this real quickly. There's a couple ways that we can envision this, but let's do a very simple exercise. Paul, I'll pick on you because you've been talking. Paul, you are younger than me. And I can say this statement: Paul is younger than Ryan. That is a fact. It is true. But I can also say that fact in a different way. I can say Ryan is older than Paul. So that's two ways to write the same fact. So by the fundamental theorem of calculus, I can write all of these in terms of integrals. So let's do that. By the FTC, we know that the velocity is the integral from 0 to t of the acceleration. Let's say ax dx, which becomes the integral from 0 to t of negative, let's use 32 dx, which becomes negative 32 x evaluated from 0 to t, which equals negative, I got to be a little careful here, negative 32t, excuse me, minus 0. The 0 goes away, so we'll just ignore it. I guess I should be a little careful, be more careful. I sort of misspoke. I'm forgetting, I forgot one thing. So this should actually be v of t minus v of 0. So it might be a little bit backwards for you to think of it this way, but all we're saying is if you integrate acceleration, you get velocity. Does anybody have a question about this? So if I integrate acceleration, I get velocity. So let's look at this, what we just showed. We really just showed that the velocity at any given time is equal to the initial velocity minus 32t. Now, we were told what the initial velocity, what was it? The initial velocity was what? 100. I mean, that's what we were told. We were told that when it leaves your hand, it's moving at 100 feet per second. Does anybody have a question about this? Now,
I'm sorry.
yeah.
Where did The 32t.
Okay, so if you go back to the previous slide, we're trying to integrate negative 32, right? So
Right.
what is the antiderivative of the number? It's just the number times the variable. So I get negative 32 times the variable. Now I have to plug in, I have to evaluate it at t and 0. But I first plug in
I'm
t. What's that?
I'm sorry. My internet is kind of terrible and it's spaced out for a second. I get the steps. I was just wondering where the number 32 came
Oh, that
from.
comes from, you go back one more, that's the acceleration of gravity. That's given. So
Oh,
you
okay.
can't do this problem unless you assume that gravity has a certain acceleration and it's either 9.8 or 32. But since the
Right.
problem was, does that make
I'm
sense?
just so you sorry. I'm just so used to seeing it in metric. I didn't realize it was converted to
Yeah,
English.
you know why? You know why we like to keep it in feet for these baby problems? You'll see why in the next step.
Okay.
Because the number turns out to be sweet and nice. But you're right. Typically, most humans use 9.8. But somewhere along the line, the British confused us when we got our independence. And like fools, they tricked us into some stupid thing we thought was cooler than the metric system. And boy, were we wrong. No wonder most, I shouldn't make broad generalizations, but most of us stink at like basic numbers and in measurements. It's because our system is so foolish. The metric system's so simple. Everything is in tens. All right, anyhow, that's not neither here nor there. Okay, so we're going to do this again. We're going to repeat the same process, only now we're going to do to get the height. So we repeat for the height. So the height at any time minus its initial height is the integral from 0 to t of the velocity function. But what's the velocity function? The velocity function is just that one above. And so if we integrate it, you get 100x minus, now this is why I use feet, because if I integrate this, I get 32x squared over 2, right? From 0 to t. And when I plug in 0, everything goes away. So what remains is 100t minus 16t squared. And so by choosing 32, I get half of that to be 16, and that's cuter than 9.8 over 2. So this is actually one system where the metric system is not the best. No, I'm just kidding. Now, we're told in the problem what h of 0 is, the initial height. If you look at this, this is our initial height. This is equal to 3. So here's what we can conclude at the end of the day. Here's what we concluded. So, and this is pretty nice. The height is negative 16t squared plus 100t plus 3. Now, if you're being very observant, you're going to look at this and say, huh, interesting. I see 103, and those are the numbers that showed up in the problem. And the answer is, duh, yeah. There was nothing special about 100, and there was nothing special about 3. I could repeat all this in general, and so it might be worth our while to do that right now. So in general, if initial height equals, we usually use this subscript, h naught, and initial velocity will denote it v naught, then the height at any given time is negative 16t squared plus v sub 0 times t. That's a t, not a plus. Let me fix that. These plus signs and t's, I'm confusing you guys. I feel bad. So that's where that formula comes from that was poured down your throat in algebra class in high school. Consequently, I think it was Galileo that was one of the first people to realize this pattern, that falling objects were proportional to time squared. So when I say falling object, there would be no initial velocity. It would be 0, and then the height would be whatever you wanted it to be. How high are you dropping it from? Does anybody have a question about this? Maybe not, maybe not. I get some water. You guys think about asking a question? Anybody chatting it up? No chats, that's good. Just O'Grady. It turns out this is anything that moves along a line can be described and it can be analyzed in this manner. There's lots of things that move along lines that you don't even realize it. A very simple illustration is something maybe you saw in physics. Although you guys maybe did something. Didn't you guys use, if you took physics, you might have had those experiments with the air tracks, maybe, I don't know. Or maybe you've seen a spring hanging, and if I have a mass and I pull it, then the mass oscillates up and down. Well, we can describe that physical phenomenon with stuff like this too. And don't forget, many things in the world around us can be modeled by springs. Anything that oscillates, I mean, there's obvious ones like the suspension in your car that goes like this, you know, suspension on airplanes when it lands. So these things that oscillate turn out to be sort of everywhere. And the more math and physics you learn, the more you realize that. Yeah, think about your heart rates in many ways can be thought of as an oscillation. Boom, heart beeping. All right, anyhow, let's not get too out of control here. Does this make sense? Does anybody have a question about 10? Oh, you did the tracks, Paul. Very good. Yeah, I figured as much. All right, so all the other problems are area problems, except for the syllabus one. So hopefully you read the syllabus and answer those questions. Cool. You might be curious to why problems 1, 2, and 3 are there. Well, again, I can't emphasize enough how important it is that you understand the definition of the integral versus how we're computing them, because that's going to be a big theme the remainder of this semester. The fundamental theorem of calculus gives us a method for computing integrals. But it doesn't work all the time. It only works in certain scenarios. And we're going to study those scenarios in this class. But there's other scenarios where it doesn't help you. And we'll talk about those later on too. And then that gets us into things like approximations and stuff. It's going to be fun. I'm excited. I love Calc 2. It's like my favorite subject. Well, not my favorite subject. I shouldn't say that. It's one of my favorites to teach. Any questions about this? By the way, there's more. We're going to use one of the problems, and I guess this helps us transition, is we often think of the integral as area. And if you go back to what I said on Tuesday, area is only one of many interpretations of the integral. Depending on context, we can interpret integrals in many different ways. The next thing we're going to see is we can interpret them as volumes. We're going to also find that if you've had physics, you know what this word called work is, work done. In order to compute work in a general place, it requires us to integrate. If you want to know how much work is done by an elevator, lifting an elevator up and down, that requires integration. If you want to study certain forces, like the force of water against a wall, which is important when we're constructing dams or building swimming pools, that requires integration. So we're going to talk about some of these applications, probably, well, not today, but next week. Does anybody have a question? Okay, so what's next? I think we should motivate what we're going to do next. And then those of you who have finished this homework can start on it, and it's not, give you something to look forward to. So let's transition then. So here's the idea. Can we generalize our ideas of area to answer questions about the size of solids? So let me talk right now briefly about what I mean by our ideas on area. I want us to think of the theme here, not necessarily the specifics of the integral, but the theme. So it's worth thinking of it this way. So let's take and review this idea. So hitting the wrong. So what was the key idea? We take the object of interest. In the previous case, region in the plane. And chop it into small pieces. That's what we did. So let's sort of draw that again. We have some curved region. And we chopped it into little pieces. So maybe I'll use red here. And what we did is we approximated each piece with a rectangle. And so what this idea did is this idea motivated the Riemann sum. So that was the key idea. We have some region, we chop it up into pieces, we look at one of those pieces and we say, okay, let's approximate it with a rectangle. And then we know the size of a rectangle. We know that its area is its length and its times its width. And so then if we get one of these small rectangles and we keep making them smaller and smaller by chopping it up into more and more pieces, then we got this limit happening. And that limit was given a name. It was called the integral. And so since it worked with plane regions, we think it should work with solids. So we think this idea should work with solids. So let's take a specific example. Imagine a bullet. So what might a bullet look like? I'm going to draw one that looks like this. So it has some sort of imagine that I have this object, or something more concrete. Imagine I have a cylinder, like this can is cylindrical. What I ask myself is, can I chop it into small pieces and get information about the small pieces? So if we chop it into small pieces, what we can do is we can approximate each piece by a simple solid. So that's the idea. Can we approximate this thing by, okay, let's take a knife and let's slice it up into a bunch of little pieces, but can we slice it up in a systematic way where we can easily compute the size of the slices? And then if we can easily compute the size of each piece, then we can add them all up. And if it's a Riemann sum, we imagine that adding them all up is not hard because it can become an integral. So it turns out that we can do this. So this can be done for many solids, provided, notice I didn't say for all, I said for many solids, provided we agree on some basic definitions. The first one is volume of a box. So if I have a box which looks like this, it has a length, it has a width, and it has a height. If we all agree that the volume here is length times width times height, we're good. So if we make this a definition, if we say any object that looks like this, any solid that looks like this has that volume, then we're going to be able to make a more general definition of volume. And then the second thing we must agree on is the volume of a cylinder. So what does a cylinder look like? It looks like this. Well, that was pretty bad. Let me. So this guy has a height, and it also has a radius for its top and bottom. So if we agree that the volume of a cylinder is pi r squared h, then we're golden. So we got to make these assumptions. Or I don't want to call them assumptions. We have to agree that these are reasonable definitions, and we're going to make this a definition. The volume of a cylinder is given by this. And then there's another special case of this. That's if we drill a hole down the middle. I spelled that wrong. So we have to agree that this is, if we take this creature and we take a drill and drill a hole down the middle of it vertically, which we'll call this a cylindrical shell. So what does that look like? That looks like So imagine here's our cylinder, but we're going to drill a hole out of it. And so when you look inside, it looks like this. So it's hollow. Now, what is the volume of what remains here? So this is a little trickier. One way to think about this is to take a knife and cut vertically. And if you lay this thing out, if you lay it flat, so let's call this its height. And it's going to have some little thickness here. We have to sort of imagine that there's an inner circle and an outer circle. So let's say that it has some thickness. So if we cut it and lay it down, it's going to look like a slab, like we had on the previous page. So here's its height. What's its thickness? We'll give it a name. I don't know. Let's call it D. And that's not a good D. And then it has a distance from here to here. Well, what is that distance? Well, if you think about it, it's 2 times pi times the radius of this creature. And so you might have to convince yourself of this. And so what's the volume of this? The volume of this is 2 pi r times d times h. So if we all agree that these three shapes have volumes, if we define them this way, now what we're going to be able to do is define the volume of even more general shapes. Does anybody have a question about this? Comments, questions? All right, then what we should do is we should end this. If you have any questions, please ask right now. Otherwise, I will upload all this to the interwebs, and then I'll give you some new work to start working on, and some material to help get us started for what we're going to do on Tuesday. Any questions, comments, concerns? All right, I will stop recording now. If I don't hear from you guys through email or anything, I guess have a good weekend, and I'll see you Tuesday. Be safe.